This is the first of a series of videos dedicated to chemical equilibrium. We will be describing what is equilibrium and how a systemic chemical equilibrium looks like. We will define the equilibrium constant and describe its applications, and we will perform calculations involving equilibrium constant and concentrations at equilibrium. And finally, we will discuss Le Chatelier's principle, and we will use the Le Chatelier's principle to predict changes to the equilibrium. And this is just an introductory session because it will be exploring with much more detail chemical equilibrium when you are studying it in Introduction to Physical Chemistry and Thermodynamics. As usual, this video has been split into several sections to make it easier to follow. When we look at a chemical reaction, one of the things we're interested in is the yield of a product, the yield of the reaction. And that is the ratio of the amount of the product we have obtained to the amount of product we were expecting if the reaction were to go to a completion. And ideally, we would be aiming for 100% yield, which means that we are getting as many grams of product as we were expecting if the reaction was were to go to completion. You can also look at the yield as, for example, sometimes we do not have reactions with reagents in stoichiometric proportions. Very likely, sometimes we have one particular reagent that we're particularly interested, and we call that limiting reagent, the one that in this case could be in the smallest quantity, in the smallest ratio, and all the product will be dependent on how much of that that reagent we have. So you could also define if you have a reaction in which you are not using stoichiometric quantities of all the reagents, but you have one in a particular low quantity with respect to how much you would need, the limiting reagent, as a ratio of the product obtained to the amount of the limiting reagent or the key reagent that you have. So in an ideal world, we would expect our reaction to have a yield of 100%. However, in practice, that doesn't happen. So, and the yields are lower, in many cases, much lower. So why wouldn't the actual yield of a reaction equate to the theoretical yield predicted from the chemical reaction equation, from the chemical equation and the proportion of the reagents and the stoichiometry of the different reagents? Well, sometimes there are impurities in the reagents, so actually the number of moles of a particular reagent you think you have is not quite correct because some of that will be impurities. Sometimes there are leaks to the environment and the reagent or the product might escape. It could be, for example, in the case of a gas. Sometimes you have undesired byproducts, side reactions that impact your ability of your reagents to react to produce the product because they are engaged in those side reactions. And sometimes the problem is that the reaction you're working with is a reversible reaction. It's a reaction in which the stability of the products is not that much, not that much compared with the reagents. So at some point, when you have sufficient products, they start reacting with each other to produce back the original reagents. Some reactions are what we call irreversible. The products do not react back to give you the reagents. An acid hydrolysis, a gasification process, a combustion process. You can be absolutely sure that if you are burning, if you are making react an alkane or a general hydrocarbon with oxygen to produce CO2 and water, the CO2 and the water will not react back to give you your original hydrocarbon. However, other reactions are what we call reversible. The stability of the products compared to the reagents is not that great that at some point, when the products are in sufficient quantities, they start colliding with each other in an effective manner to give back the original reagents. And many reversible reactions are very useful. For example, in the industry, the Haber process to produce ammonia from nitrogen and hydrogen is a chemical equilibrium. It's a reversible reaction it's a difficult reaction. It requires a very high pressure and a high temperature. It is a catalyst, and even with all that, the yield of that reaction is only around 15%. Another example is, the production of sulfuric acid. Quite a few of the steps of the production of sulfuric acid are irreversible, but the specific conversion of the step of converting sulfur dioxide into sulfur trioxide is a reversible process. So just because a reaction that is reversible doesn't mean that it's not useful. It can be very useful, but it is difficult to obtain product in sufficient quantities, or it becomes more difficult to obtain as much product as possible, and it requires a careful control of the conditions of the reaction, the concentration of the reagents, the temperature, the pressure, etc., for that reaction to take place successfully and to produce an appropriate yield. And a lot of this video will be about how to play with those conditions to achieve the best possible yield for that reversible reaction. Chemical equilibrium is what we call a dynamic equilibrium. If you look at the figure at the top, these two people sat in a seesaw. That's a physical equilibrium, and none of those two people are moving. However, when you have a chemical equilibrium, the reagents and the products are reacting all the time. It's just that they are reacting at the same rate, and what you see is a sort of a steady state, which particular concentrations of reagents and products. So if you plot the concentration of reagents or products with respect to time, a typical reversible reaction will have this shape of the graph. Initially, you have all reagents and not products. In the early stages of the reaction, the reagents react fast to produce products, and so your amount of reagents will decrease as the concentration of the products will increase. At some point, you will start having more and more concentration of products and less concentration of reagents. And at some point, you will have sufficient amount of product and sufficiently low concentration of reagents that the collisions will start not only being between the molecules of the reagent, but the molecules of the products will start colliding with each other and eventually break down to produce the original reagents. So the reaction is reacting all the time, but the forward rate, the speed into which the reagents produce product, equals the back rate, the rate to which the products react back to produce the original reagents.